Okay, in this video I'm gonna talk about Mistral model, and I'm gonna explain what Mistral LLM is and how different it is from transformer model. We will do llama later on in another video, and the way that it works, the way that this video is going to be is that first I'm gonna explain quickly what Mistral is and how it works, and right after that, and also a kind of comparison with transformer model. Right after that, I will explain a little bit about some features of the Mistral as you can see in this table, and right after that, a quick explanation of the in fact Mistral code, which we will go through that in a minute, and it is a very quick and high overview. And right after the high overview, I'm gonna explain each block and each part of the Mistral in much more depth, including the mathematics behind each of these blocks, for example, RMS Norm, or I don't know, the sliding window attention, rolling buffer, mixture of expert, so on and so forth. And then also coding each part together with some numerical examples. So, okay, let's just jump into it. So about the Mistral, so what I would like to first explain here is the difference between Mistral and traditional transformer model. So as you can see in Mistral, so technically we have the input first of all, and right after the input we have the embedding. So the embedding size, as you can see here in this table, so the size of the embedding or dimension of the embedding is 4096. And right after the embedding, what we have is RMS Norm. And as you can see, this is technically one of the difference between Mistral and transformer model. So as you can see, right after embedding we have the RMS Norm here for Mistral, but for transformers, and also it is the same for llama as well. Llama and Mistral are pretty much similar to each other, but for transformer, as you can see, we have the norm right after the attention mechanism. So this is one of the differences technically. And again, back to Mistral, after the RMS Norm, as you can see, we have query, key, and value. And the thing is, for query and key, we have a positional encoding, which is called Rotary Positional Encoding. And again, this is another difference between Mistral and transformer. So in Mistral we have rotary positional encoding, but in transformer we have positional encoding, which is a kind of a mixture of sine and cosine, I can say, equations for transformers. But once we calculated the positional encoding for query and key, we will give them into the attention mechanism. But the attention mechanism in Mistral is a little bit again different. So what we have in Mistral is we have a sliding window attention together with KB cache and group query attention and also rolling buffer. So all these will allow us to make it much more optimized and reduce the number of calculations. So for example, KB cache allows us to avoid repetitive calculations for key and values. Or for example, a sliding window attention is a kind of attention that, for example, for each token we are allowed to, let's say if the window size is full, it will allow us to just look to the last four, in fact the previous four tokens that we have. So this is again one of the, I can say, inventions of the Mistral model. And right after that we have this skip connection, which we will add the information from just the step before the RMS norm. And after the RMS norm, what we have is a mixture of expert instead of feed-forward layer. So usually we have feed-forward layer, as you can see here in the transformers, but here we have something called mixture of experts. Mixture of experts is, just imagine it as a bunch of feed-forward layers together with something called gate. So gate allows us to in fact redirect the incoming input or token to number of or top k of the experts. It's just, imagine the analogy for that would be something like, imagine you're going to, I don't know, for example, hospital, and so hospital has lots of doctors, and you might have a specific, for example, let's say pain in stomach. So what you do is you go to receptionist, and receptionist will talk to you, and then receptionist will redirect you to the expert who you need to visit. So this is technically what mixture of experts are. And then after mixture of experts, we have again RMS norm and linear, and then softmax. And about those features, about the numbers, as I said, the dimension size is 4096. The number of layers, so as you can see, we have n here, so the number of these blocks on top of each other for both Mistral and also Mixtral, it is 32. The head dimension is 128. The hidden dimension, the feed-forward network, is this number 40,000 and something. The number of heads is 32, and the number of KV cache heads, which is kind of, we can call it group query attention, is 8. So what it says is, instead of having one query, in fact one key and value for each query, what we do is for every 8 query we have one key and one value. So imagine by how much we reduce the number of calculation. So every 8 query will share one key and value. And again, this is a forward and very quick explanation about Mistral. After this, we're gonna dive deep into each section and in fact module in further details. So you can skip this part if you like, and you can go to each part that you wish. And also about the window size, it's also 4096, which is a kind of rolling buffer, which allows us to do a kind of cycle through the incoming inputs. And the context length is for Mistral it is 8192, for Mixtral is 32k. The vocabulary size for both of them is 32k. The number of experts, so Mistral doesn't have any experts, but however on the implementation you can see the in fact mixture of experts, and you can see that whether you want to turn it on or off. But for Mixtral model it is 8, and the number of experts per token for Mixtral it's 2. However, again, you can tweak all these parameters and see change it to whatever you like technically. Just quickly, let's jump into the code, and then after this code we're gonna dive further deeper into each block and part. So what we do is, technically we do a bunch of imports. We have something from functools, we have partial, and what partial does is, imagine that you have a function, and this function has a couple of input variables. Partial allows you to introduce couple of inputs. For example, let's say if your function has 10 parameters, with partial, you can introduce 2 parameters and leave the other 8 for later on. And we have also some imports from typing. For typing, we have torch, we have xformers. From xformers, we import technically the block diagonal mask, and also from Mistral Inference, we have from the arguments, we have LORA arguments, and we will see all these in more detail later on. We have the cache view, which is for technically for in fact cache buffering. We have LORA, we have mixture of experts, and also rotary positional encoding. So at the first place, what we do is we define a function called repeat kv, and what it does is technically it repeats a tensor in a certain dimension that is given. So imagine that we have a tensor called keys or values, and I can say repeat the number of repeats in a certain dimension. So what it does is technically, given a tensor, it will repeat it in a in a number of times that I say in a dimension that I specify. So technically, when it comes useful, it's for the KV cache, the group query attention part. And after that, we have something called LORA. So the thing is, for each of these parts, we have, as you can see, we have different layers. For example, this linear layer or feed forward in the mixture of experts. So what we can do is we can have them as LORA for further fine tuning, or we can simply just put a linear layer for them. So this maybe LORA function allows us, when we in fact put the when we specify the LORA arguments, we can have LORA linear layer, or if not, it would be just simply simple in fact feed forward layer. Back to attention, which we have it right here. The way that it works is, so technically again we have number of heads, number of dimensions, the KV heads, and number of repeats. What repeats means is exactly as I mentioned earlier, it is just the number of in fact the number for group query attention, so which in this case would be 8, and the scaling factor as well. So what we can do here is, again, we use maybe LORA, and we specify the LORA arguments. If it is none, so it would be simply a linear layer. If not, if we want to do, for example, fine tuning for Mistral, it would be the in fact LORA layers. So we specify that maybe LORA for each of the in fact weights for query, key, value, and the output in the attention mechanism. And the forward pass would be simply the input for forward pass would be the technically the X, the input to the model, the frequencies. These frequencies, what are these frequencies? These are technically the frequencies that coming from rotary positional encoding. And again, if you want to further understand what these frequencies are, you can just go to the rotary positional encoding section. And then we have cache, which is a cache view object. We have the mask, which is optional, and also we have the sequence number and how many sequences do we have in our batch. So what we do, we technically multiply the input to each of those weights that we specified up there, and then once we have them, we can give them to rotary positional encoding. So this part would technically be specifying these before applying rotary positional encoding. And then once they are done, we give them into rotary positional encoding. And here in the cache, what this cache says, so okay, this part we are right here. We're not done, we're not yet into the attention mechanism. But imagine that you're talking to a chatbot, or you're writing a prompt for designing a chatbot. We have a couple of scenarios. What are those scenarios? So one of them is, so this part technically covers all those scenarios. So it says if the cache is none, just do the, in fact, get the key and values and put them and turn them back into the model for calculating the attention. But when cache is none, so technically that's when we want to do the, for example, training, when we have literally nothing. But so that's one case. The other case is we can prefill the cache. What is that prefill? So imagine that you write a prompt. For example, you want to design a chatbot and you have a prompt. This prefill is exactly your prompt, which will prefill the in fact cache and buffer for you, and then you will update it with the incoming in fact key and values. And the other one is just simply when you stream or talking to a chatbot, you get the queries, and so you need to generate and update the whole in fact process and scenario. So the third part is that scenario that I just told you. And then once it's done, once we calculated all those key values, we give it to repeat KV. And don't forget, what was the repeat KV? It is technically a function for calculating the group query attention. And once that part is done, so we are ready to calculate our attention. So this is technically just a memory efficient attention, which we can see it as, for example, something like sliding window attention, so on and so forth. And once the attention has been done and calculated, we check if it is a tensor. In fact, the output is a tensor, and then we just turn it back. We multiply it to the weights and turn it back to the next section. And so that part, the attention part, as you know, is just right this part. And after attention, we have the feed forward layer, which is technically just again a bunch of LORA layers. And don't forget, the maybe LORA is if you specify the LORA arguments, it uses the LORA for fine-tuning. If not, it would be simple feed-forward layer. So it is technically, it will get the input and the dimension with the dimension, and then we have a hidden dimension. We will technically expand it and then shrink it to extract some features and information out of it. But the important part is we need to also mention once we get the input from this in the forward pass, we give it first to the W1 layer, and then we have SwiGLU activation. This is one of the technically differences, also other difference between Llama and Mistral against traditional transformers. So this part was a feed-forward layer, which we had it right above here. The other one is RMS Norm, and RMS Norm is technically, again, if you want to furthermore understand about its mathematics, go back to RMS Norm section. So here we just simply calculate the RMS norm, and we just do the what's that, SQRT, the reverse SQRT of that, and we do the mean for each of the elements of the tensor, and then we just simply calculate the RMS norm. So these were all the blocks or layers in the Mistral, and when we want to technically make the whole block, what we have the dimension, we have the hidden dimension, number of heads, number of KV cache, head dimension, norm for norm epsilon for RMS norm, which is a small epsilon in order to avoid effect division by 0. We have LORA arguments if we want to do a kind of fine tuning. If not, there's no need to specify anything. And also the mixture of experts if we want to use mixture of experts right here in this section. If not, that would be simply a feedforward layer. So what we do, we first initialize them, and then what we simply have is just in the forward pass is just simply we have the input, we give the input to the attention together with frequencies and the cache, and once we have all of them, we can calculate the attention, and we add a skip connection to that attention, calculated attention. Don't forget it. We have this skip connection here, and we add it to the attention. And after adding that to attention, we give it to the feedforward, in fact, neural net. And again, another skip connection, and finally the output. So technically this was, as I said, this was a very quick explanation of what Mistral model is and how different it is from Transformer. But if you like further more details, in the next sections, I'm going to explain, for example, what RMS Norm exactly is, what the KV cache is, oversliding window attention, or how rotary positional encoding works with detailed mathematics, and also the code and some numerical examples to understand it better and better. So yes, the next section would be about rotary positional encoding. Okay, now in this section, I'm gonna talk about, in fact, the encoding of the Mistral, which is called ROPE, or Rotary Positional Encoding, and as you can see, it is right here in the architecture of it, just these little circular symbols. And what will happen, we will add them and apply them on top of a query and key. But yeah, let's see what are they and how they work. So technically we have two main kinds of encodings, which one of them is the simple positional encoding or sinusoidal encoding, which mainly is being used in Transformers, original Transformers in Vaswani et al. But the ROPE or rotary positional encoding is mainly used in more modern language models like Llama, GPT, DeepSeek, and Mistral as well. So it is much stronger in terms of maintaining relative positions and also long context, which is very useful in these language models because we want to have larger context window. And also it scales better, and the way that it works is, so in the previous version, in the simple version, it is just adding sinusoidal vectors, learned vectors, but here we rotate the Q and K vectors using the complex numbers and complex exponentials, and we will see what that means in a minute. And yeah, just it's a little bit harder to understand maybe because of its implementation, but we will dive deep into that and we'll see that how it exactly works. So yeah, feel free to have a look at its paper, rope or rotary positional encoding. And on the paper, this is technically the final equation that we have for rotary positional encoding. But what this exactly means, and if you want to have a look at how we get here and how we finally arrived to this kind of equation, you just have a look at the paper. I'm not going to explain it here. It is a little bit more detailed than what I want to do here. So yeah, what this means is technically it is just the rotation with the frequency vectors of theta in the position of the m, and this d means the dimension of the embedding. So technically what we have is, imagine that we have a sentence which contains of wi's, and each w is just, let's say, a word in the ith element word, and we have also the embedding of each of those words, or the, let's say, not embedding, yeah, we can say embedding of the token, which the dimension would be d here, and the thetas, or the frequencies we can call them, or angles, are just the length of the vector is half of the dimension, and we will find out why is this happening. It is from theta 1 all the way up to theta d over 2, and the way that we calculate them, those thetas, is just theta I would be 10,000, and this 10,000 is the constant. We can change it, but usually on the code it is 10,000 to the power of this whatever that it is. As I mentioned, the d is the dimension vector, embedding dimension, m is token position index, and xi, each of the xi's are the dimensional word embedding of the ith token. Okay, but this might be a little bit overwhelming, and how we can literally calculate this on Python code. It might be a little bit, might look a little bit hard and overwhelming, but there is a really good trick that how we can turn this into much easier format and much optimized format and calculate it. Just to give you a hint before diving deep into that, just imagine if we select each of these pairs, this would exactly be the complex number multiplication with Euler, let's say, representation. So what exactly happens? Just imagine that we have C in complex numbers, a complex number, complex numbers, this Z, and it could be something like x plus iy, let's say. Theta is just the angle or a real number. For Z, the complex rotation by angle theta would be defined as this equation right here, which is Z times E to the power of I theta, which is Euler representation for complex numbers, as you might know, and which would be the same as Z times cosine of theta plus I sine of theta. And again, as I said, if we imagine Z is x plus iy, if we multiply that to this, it's exactly the same as saying that we multiply this matrix to the vector of xi and with x and y. And yeah, that's technically what will happen. And so with a little bit calculation, which I'm not going to go into detail, again, you can refer back to its paper, we can understand that this matrices, and by the way, this sign is element-wise multiplication, this whole, all these matrices, we can simply represent them as this diagonal block diagonal matrix, which each of these are m theta i's can be seen as cosine m theta I minus sine, and cosine of m theta I. And we can simply achieve this block, this part, by multiplying this cosine and sine to x1 and x2, let's say, for this case, which again would simply be this equation, the same as this equation right here, because complex numbers are literally the same thing. So an example for that would be, Just imagine that we pick d equal 4, and position would be m equal to 1, and we have because we have d equal to 4, so the embedding dimension would be 4, so x would be, let's say, something simple like 1, 0, 0, and 1. So what we need to first do is we need to compute the thetas, and again, going back to the equation, how the thetas look like is just simply this constant to the times of that equation, or whatever that is, for I from 1 all the way up to half of the dimension for so in that case, in our case, because these two we only have two in fact two frequencies, or let's say thetas, theta 1 and theta 2, which is theta 1 is equal to 1 and theta 2 is equal to 0.01. Then we need to calculate the frequencies, or let's say angles, which are m theta i's for all m and all thetas. And this is exactly how we calculate them, and we get the cosine and sine of those. Now, what we can do, as I said, we don't need to, in order to achieve this big matrix and big equation here, we can simply put them and divide them 2 by 2 in tuples or pairs. So in our case, since we have x equal 1, 0, 0, 1, we can divide them into 2 tuples or pairs, and then we can literally calculate them with the help of complex numbers, which is technically the same as this matrix here. For the first two, the pair 1 would be 1 and 0, and we can literally multiply them by these cosine and sines, and the same thing for, in order to get x1, rotation of x1 and x2, and the same thing for the second pair, which is x3 and x4. So technically we will do all this for whatever our embedding is. For example, in the case of Mistral, which the embedding, I guess it should be 4096, so we should do all these. We should technically turn this into 2 by 2 tuples and do the same equation for all of them. And this would be the result right here. And then we concatenate these two results, and we will have the final output, as we can see right here. So what we had the embedding right here, which was technically 1001, but now we have this much informative, I can say, if I can finish this, yeah, we have this much more informative vector, which has the positional in fact information of the vector and the token, not only for itself and absolute, but also relative to other tokens, which is very useful in the technically language models. But what this means in the code, so this is the rope code from Mistral itself, and you can find all these information, the PDFs and the code itself, in my GitHub repo. I will put the link for that right down below. I just added a little bit more doc strings and also some comments and explanation to understand it easier, but yeah, let's dive deep into that and see what's exactly happening. So the first function, it has two main functions. The first one is just pre-computing the frequencies or the angles, and the second one is applying the rotary embedding. So what will happen in the first function is, what we have as input is the dimension, and which end here means the sequence length. So technically this is those m's, and the theta, the constant theta, which you can turn it, but usually typically it is 10,000. So first we can calculate all those frequencies, which this line is technically the same as here, just calculating all these, and then we have all of the m's here, because we don't want to calculate them one by one. So what we do, we have all the m's here in a form of a vector, so that would be a vector of from 0 to all the way to t, or m, we can say. And then we can do a outer product to get all those. Technically right here it would be angles m theta i's for all m's and thetas with this operation, with this line right here. And the shape of it would be end and the half of the dimension. And we can technically turn them into the polar format because we want to have them as a complex numbers for doing the complex multiplication. What next we do, we apply them. But if you remember again from the architecture, what we had here, we need to apply those the rope into K and Q. So we will, as an input here, apply rotary embedding. We will have the input tensors of the query and key, and also at the same time the frequencies. So here we can turn in fact query and key into complex numbers to do that complex operation. And remember, the shape of them is the sequence length, badge, and half of the dimension. So it has 3 dimensions, but the frequencies we had, in the frequencies we only had 2 dimensions. So what we need to do, we need to add additional dimension into that in order to be able to match them and do that multiplication easier. So once we turned query and keys into complex numbers and add this additional dimension, what we can do is we can do the matrix complex multiplication and then turn them again back to real numbers. So that would give us the, technically just right here, again back to PDF, doing the multiplication right here and then turning them back into real number, or let's say doing the concatenation. And we will get all the results back from this function, which is, again, we had the Q and K as the embeddings. We applied those frequencies. Now we have the positional information for all those tokens. And yes, that's technically it. And the next part would be, technically in our Mistral journey, would be the RMS norm and embedding. Okay, in this part I'm gonna talk about RMS norm, which, as you can see, we have a couple of in fact, in a couple of places in Mistral we use RMS norm right here and also right down here and within the attention module, just right after attention module as well. But what is RMS norm and what it does? So technically RMS norm stands for root mean square layer normalization, and it's kind of a simplified version of the layer norm. Why? Because it kind of reduces computational complexity, and the reason that it reduced that complexity is because instead of using or adjusting the distribution with mean and variance, we simply use root mean square to kind of do a element-wise, I can say, adjustment. So what is the technically difference? What are the differences between RMS norm and layer normalization? So in terms of features, for example, the mean subtraction, layer norm has that, but RMS norm, there is no subtraction. At the same time, there is no variance because we don't need to calculate variance. It is much simpler. We simply use root mean square. And also, as I said, in terms of computation, it is much lower than layer norm. I think it should be something around maybe 30%, which is pretty good. And stability, it's slightly less stable, but we can do a couple of tweaks to make it better, and especially in long and deeper attention and attention network, it works much better. And yeah, so these are the main I can say features of RMS norm. And in terms of advantages, as I said, it is much faster and fewer floating points operation, and as I mentioned, it's much better, it works much better in very deep transformers like Mistral or Llama or any of these giant language models. So how it looks in terms of mathematically, so imagine that we have an x or a vector in d-dimensional vector, or we can just simply see it as a embedding in d-dimensional vector space. So for layer normalization, what we do, we need to calculate the mean and variance and then subtract each of the elements of that vector from mean and divide them by variance to kind of readjust them, readjust that distribution. But and there are a couple of learned parameters, but here in RMS Norm, all we do is simply we use this equation, which you might have seen in RMS error or something like that. So yeah, as you can see, there is no subtraction and there is no mean calculations, but how it looks like in terms of floating point operations. So imagine that we have a vector size of d, or let's say we have an embedding of within a vector space of dimension 500. So we're going to count how many operations we need to do a layer norm on that, and how many operations we're going to need if we want to do RMS norm. So according to the equation, so we need to calculate the mean, subtraction from the mean, square differences, sum of the squares, divide by d and add epsilon, I don't know, a square root, divide each by standard deviation, and then gamma and beta. So as you can see, we have all these operations, and technically once we do all that, it would be something around 4,000 floating point operations. But on the other side, if we want to do the same thing with RMS norm, as you can see, it simply is, if I can adjust this, yeah, it's simply just a square inputs, sum of the squares and division, and that's it technically. How many operations? 2.5k, which is pretty good, as I said. So it would be something around, let's say, yeah, 37.5 fewer operation, which is just massive. It's a lot of operations, fewer than the normalization. And yeah, as I mentioned, this is how it looks like in terms of the mathematics behind it, and it's pretty simple. And if you want to just go back to the code where you can find it, where you can find the RMS norm, is technically on the Mistral code. You can just go under transformers layers, and by the way, I will put all these into my GitHub repo together with the PDF so you can have a look at it. And if you want to find more details, and as you can see, so the RMS norm here, it is simply just defining the epsilon, defining the learned parameters, and then what we need to do is simply we need to calculate that square root of the vector. And the reason that we are using torch.rsqrt, it is the reverse of the sqrt. So that's technically, as you can see, this RMS and this sqrt is under this what's that, x is over that, so we need 1 over RMS. So this is exactly what it does, and it makes that 1 over sqrt for us. And then we calculate the mean, and the reason that we have -1 is because we want to do the mean for features, based on the features, which is technically the last dimension here, and we will keep the shape of the tensor as it is without any modification. And yeah, finally on the forward pass, we just passing a tensor and we do the norm and just simply calculate and multiply that by the weights. And yeah, technically that's it for RMS norm. And so technically the next step would be, I think, the attention module. And yeah, the group query attention and the sliding window attention. Okay, in this section we're going to talk about the sliding window attention, ruling buffer, and KV cache, which we all use all of them in more modern LLMs like Mistral, Llama, and even DeepSeek, and so on and so forth. But yeah, let's jump into it and see what are they and how they perform. So about the sliding window attention, it's just a kind of attention that allows you to do the attention but with less computation. So imagine, I don't know, we have the just about these diagrams. Imagine that we have keys and queries, and also imagine, for example, I don't know, imagine that we have different tokens and they attend each other. So one way of doing that, the attention, is each of the tokens or keys can attend each of the queries, which we call it full attention, which technically is a little bit, I can say, nonsense, because we don't usually use such a thing. We mainly use causal attention and a sliding window attention, and the reason that we have causal attention, as you can see, the tokens they attend anything that is before the current token. So we don't go further because there is no point of going further, because, for example, in many of the transformers or LLMs, they are generators, so they generate something, so there is no point of looking forward, so there is no reason to look forward in the attention. That's why we put a causal mask and we literally turn all the future, let's say, tokens into 0, so we can predict what are the next tokens. And there is another version, but as you can see here, as we go forward through the, let's say, sequence, we have more tokens to look at, which can cause I can say too many operations, or it's not very efficient. But about the sliding window attention, imagine that we have a window size of 4, and as you can see, each token just only attends the previous 4 tokens, and that's why we call it sliding window. The window size is 4, but so it's very efficient and optimized. But you might say that, okay, if we only look at the previous 4, for example, let's say here in the last one, if we just look at the previous 4, how the hell we can have the full context of the previous tokens, which I will explain in a minute. The other version of the attention is dilated attention. As you can see, it is just simply putting holes into the attention, for example, attending them one by one. We attend the next 2, next 4, but not anything in the middle. It's again a kind of a strategy. It depends what you want and what you want to do and how optimized you want to make it. But yeah, you can technically do whatever you want in whichever you want. You can do a dilation on the sliding window as well. So it's up to you which one you're going to choose. But yeah, but the main one which we're going to talk about, it's the sliding window attention, and we want to see that, okay, how tokens can attend, can have the full conversation or the full context. And the key to that is just the layers. So imagine that, okay, so we have 4 layers here, and imagine we are in this very last token here, which technically attends, as we said, and by the way, imagine that the window size is 4. So technically, this token attends the previous 4 tokens, these 4, okay? And we want to see that, okay, is there any way that we can have the full context and have the full memory of what's going on in this sequence or not? So if we are in the 4th layer, we have information of these 4 in the previous layer. We get the information from all those. But the thing is, these 4, they literally have much more information from the previous layer, so the layer 2. So for example, this one, again, the last token in the 3rd layer, it has information about these 4, and the very first one here, this one, it has information about these 4. So technically we can say the last token in the 4th layer has information of all these tokens. And by the way, it is just the layers and we just repeat it. So it literally has all information of all these tokens. And if we go just further one more layer down, so again with the same reasoning, we can say that, okay, that last token in the 4th layer has information of all tokens because of the propagation of the information in fact layers, because of the data flow. And that's technically how we can make sure that, okay, we have the full context and the full information of, let's say, whatever the sequence size is, or in fact, yeah, it's a kind of trade-off, the sliding window and the number of layers. It depends on how much memory you want to have, and I don't know how much computation and optimized you want it to be, so on and so forth. But let's go a little bit deeper to even better understand it. So imagine that for that sliding window attention, and let's say the window size is 3. Let's say window size is 3 here. And imagine the sentence is, I love tennis and golf, which I do. And so, okay, the window size is 3. So this is our first layer. Then the second layer. So let's say for the first one, in the second layer, because the window size is 3, so this one would be technically what we have. This one would be the information from the previous layer. So it is I and love both of them. So it has information of both of those, in fact, what's that, positions in the previous layer. But this one, here, by a sliding window, I could simply say anything before the current token. But what I'm doing here is a little bit slightly different, and it is just for, what's that, demonstration. So the current token, when I'm saying a sliding window in the current token, what I do is I look one before and one after the token. So you can easily do 2 before or 3 before or previous token. So there is no, in fact, not much difference. So what I'm here doing by window is, if I say 3, window size of 3, I do, if I'm in the current position, let's say here, I look one forward and one backward. So here, the information that I would have is I love tennis. And here in this one, so that would be technically these 3 right here, which are love, tennis, and ant. But if we go further one next layer, so the first one again have information about these 2, so which is I love, which are again here, and tennis. So it has 3 I can say tokens or words or whatever that it is. And the second one and the third one, let's talk about the third one. As you can see, the third one, if we go one back layer, it has information about the one token, in fact one position before and after, which if we look is technically the full sentence. So this one has the full information about the full sentence. So yeah, even if we go one further layer above, so we can have even each of these in fact positions, they would have even more information and the full context of the full sentence. So that's how technically it happens. So there's no worries about if we have a small sliding window, would that affect the context or memory of my model? No, that's fine. It depends how many layers you have. So you can fix it, and there is no worries about it. And yeah, it is here we have all different types of attention mechanisms and attention types with, I don't know, the patterns and the cost of them. So for example, full attention, it's O of n squared. The causal is again the same, but the sliding window is n times w, and w is the window size. So as you can see, it is much better low memory kind of attention, and that's why we see those improvement in Mistral or Llama, which are faster and more efficient. This is one of the reasons technically. And by the way, we will go further deep with some more visualization, so bear with me. We will get to that after this introduction for all of them. So the rolling buffer, so imagine just the rolling buffer is a kind of mechanism which is a fixed size data structure which overrides the old data with new data in a, as you can see, cyclic manner. So what happens if we have a long sequence? What we can do, because of the limited memory, we can put it into a kind of circular buffer, and this would allow us to be more efficient technically. That's technically what will happen. And as you can see, it's useful in streaming data, which we have in technically all LLMs, real-time systems, and so on and so forth. Again, bear with me. I will show some visualizations which will in fact give much better understanding of how this rolling buffer would work. And also the KV cache. So what KV cache technically means is that when we want to calculate the attention and those key and value in fact multiplications, we have lots of repetitive calculation. So what we can do is we can save and cache lots of those steps and repetitive steps and avoid recalculating them. So this is technically the mathematical formulation of it, but more visually, if I want to tell you, I can just quickly go down here. Just imagine that, okay, this is the query and key of mine, and let's say okay, for example, if so these are technically the new tokens which are joining, but let's say if I can just okay, let's say if I want to calculate this position right up here, so what I need to do is technically it's just the first row, the first query times the first column or the key. Then I will get this position, and imagine that all I have is the first let's say token. So when I have the first token, it is literally this part and this part. When I generate the next token, let's say I did all the calculation and I times it to V and I get the output. So what I do is I append this back into right here and also right here. Now I need to do the next step to calculate the next step. So how that one would look like is, so now I have the second one, and if I want to get these two positions, so what I need to do is again doing a multiplication of the first row, first column here, and then what I can do is technically first row, second column, I get this result, second row and second column, which would give this result to me. But as you saw, I recalculated this part. But what I could easily do was I could simply cache that value, and that one was from the first row and the first column. And that's how KV cache happens. I don't need to recalculate this part. Or for example, if I want to imagine that I went the second flow, second pass, and now I have to, let's say, second value and second output, and then again I append it, and remember this is a generation, we just append it again and again and again, and now, and also at the same time here. So for the next one we have 3 by 3. Imagine we don't have these, technically the rest of these matrices, we only have 3 of them on that side. So now because it is 3 by 3, what I can calculate is I can calculate these positions as well. So I have total of 6 positions right here to calculate, which 3 of them, which are these 3, are just repetitive. So I don't need to calculate them. So all I need is just simply calculate these 3, and those 3 on top, I can simply add them from the cache. So this is called KV cache, and we can simply just cache all those results, and it will make the whole calculation much more optimized, and it is very beneficial. And again, as I said, there are some visualizations which I will show you in a minute, and you don't need to, in fact, I know it's hard, so bear with me, and we will go through the code and visualizations to understand it better and better. So yeah, about the visualizations, let's just quickly go here. So about the sliding window attention, so this is the code, you can have a look at it. I will put all these documents, I don't know, HTML file, PDF, so on and so forth, in the technically, what's that, my GitHub repo, so you can, and I put the link in the descriptions, so you can go there and have a look. But yeah, let's see how this technically a sliding window attention looks like. So this is technically sliding window attention together with the circular buffer for KV cache. So as you can see, let's say the sliding window, let's say it is equal to, let's say 5, and we are in the very first token. So this is the first token, and this is technically our circular buffer. And imagine, because we have the limited memory, we cannot have the whole sequence, so we have them in a circular manner. We add the next token goes to the next position. And by the way, because it is on a list, it's in a list, I can say, structure, so technically in reality it will be appended to the first I can say cell of the list. But here, because it's a circular, it is more near to reality, and what will happen later on the code, we will see that how this happens. So the next token goes to the next in fact cell, and we calculate the next token. It is on index 2, index 3, index 4, index 5, which is, again, because we have limited memory, it goes to, and it is a circular buffer, it goes to the first effect position. And again, as you can see, because we have a sliding window attention, so this is technically how it works. And by the way, we have all these in the cache, so we have all these sequences in the cache in all these positions. And as we just go forward, this is technically how it happens and how it works. So it makes sure that the calculation of the window allows us to make it more optimized with less computation, and the circular buffer helps us to deal with in fact limited memory, but at the same time being able to attend long sequences. About the in fact the attention, so which I showed you in a minute. So as you can see, this is the first, this is the full attention. So imagine we are in the second token, let's say this is the second token, and as you can see, we have all these cells calculated. So technically, for the next step, imagine if we are in the KV cache, for the next step, we only need to add that last, see, these 3 cells. Everything else is just repetitive, which we can gain it from the previous step. So we don't need, so we can cache all these values and we can just compute these last 3. For the next step, we can cache all these 6 values, or technically Q and K's. And the only thing that we need to calculate is further 4. And that's all. So this is technically the concept of the KV cache and how much more optimized it can make the whole process. And yeah, so this is technically how it happens. We just give one Q, which is the output of the previous step, and just do the calculation with the cached version of the keys. We get the scores. We have the cached V's. We generate the output. We append it back, and just this whole loop goes on and on and on. And also the sliding window, it is just again kind of representation. Again, imagine that we have the window size of 4. This is technically how the whole sliding window attention would look like. As you can see, once we're done with the 4 tokens, it will stay the same. So it is much more optimized in terms of calculations. And just one furthermore, again, if you want to have this full document, you can find it on the link to go through all the steps and how much, for example, memory it saves and so on and so forth. And this one again is just simply, again, imagine that window size is, let's say 5, the current query tokens in the window, and cached slots. So we have just only one cache slot, and this is the current one. So we go forward, and as you can see, so this is technically the step that we filled the cache, and also, yeah, we filled the cache. The next step will override it from the first place. But again, do not forget, when we override the first index, the logical sequence and occurrence of the sequence will break. So what we need to do, we need to rotate it to make sure that, for example, here it is technically 1, 2, 3, 4 and then 5, but 5 comes first. So technically we need to rotate it to make sure that the occurrence of the sequence is valid, and that's what we call it on rotate, and we will see it in the code. Just remember what it does and why we need that, because it will be appended to the first index. So the occurrence and the logical sequence of the sequence will be somehow broke. So we need to fix it. We need to unrotate it. And this just tokens, we can generate them, and this just happens on. This goes on and on and on. So yeah, let's just quickly go to the code. So what we covered was a sliding window attention, the KV cache, and also the rolling buffer. So again, I put the code, what I did is, this code technically is from Mistral itself. What I did, I add some more comments and explanations so it's easier to understand. So feel free again to get it from my GitHub. So technically what we do here, so the cache file, cache.py, explains how the cache, what is the logic behind the cache. Again, this code is a little bit, I can say, it's not that easy to understand, but bear with me. I will do a quick pass through this code, and then I can explain you in further detail with some numerical examples that makes it much easier to understand that what exactly is going on within the code. So what happens here is we have a bunch of imports, and as you can see we have block diagonal causal mask, which is technically we get the data sliding window attention and causal attention from these Xformers package library, so you can have a look at it and see that how these works. So what happens here, we have something called, the first function is something called get cache sizes, and what it does is simply says that okay, whether I want to, for all the layers, again going back to here, so for all these layers, do I want to have the same sliding window, or I want it to be different? For example, do I want to, let's say for the first layer, do I want it to be, let's say, the window size of 4, and maybe the last layer would be just 2. So what happens would be simply something like this, just only these 2. And it is very common as we go higher up in the layers, we change the sliding window. For example, the first one could be 4. It is usually like a list. It is 4, then it can be 2, again 2, and then for example something like 1 or something like that. So all it says here is okay, number of layers and how I want them to be. Is it a list, repeat this pattern across all the layers, or no, it's different for each of the layers. This is exactly what happens in this function. But cache input metadata, so this is very important for the next step, which is called cache view, and cache view itself will be directly used in the main code. We will see it in a minute. So this cache input metadata is very important. What it says, it gives a bunch of metadata information about the position of the each token, whether they should be masked or not, whether they should be attended or not, whether it's pre-filled. Pre-filled means technically is it the first round that we need to just pre-fill every position or not. So yeah, the positions are, as you can see, a global absolute token indices for rope. To cache mask, it's just it's a list of booleans, true, false, which allows us to know that okay, this token needs to be masked or not. That's how it works. Cached elements, we have the number of elements per sequence retained in cache. We will see all these in detail in the numerical example. Bear with me. This is, as I said, this is just a simple fast forward through the code. Prefill, mask, and sequences. And the sequences is just how many sequences do I have. So the way that it works is we don't just give one sequence to the whole system. So it could imagine that your system, I don't know, your Mistral, at the same time, imagine it's a kind of chat system, and at the same time you have 3 conversations. So it is 3 sequences. So you should handle all those 3. So that's why we have sequences, list of sequence length in a batch. So we have something called interval list. So what it does is just imagine we have 2 tensors. So one of them is A, B, C, whatever that it is, X, the second one is X, Y, and so on and so forth. What interval does is just put them next to each other. So A and X, B and Y, C and whatever, Z, so on and so forth. Why is this part is useful? It's useful because, again, imagine that we have several conversations. In those conversations, now imagine we have the incoming tokens. Those incoming tokens should be appended in the right order to the existing sequences. That's why we need interleaving the existing tokens, or let's say cache, to the new generated tokens that comes in. For example, you can see this as tree conversation, and when I say tree conversation, it can be 3 prompts, and these could be 3 inputs that user just started to send. So we need to give the right question or query to the right prompt, append it to the right prompt. This is why we need interleave list. On rotate, again, if you remember, this is technically what that on rotate means. When we get to the 4th position and when we have the next one, so the order is problematic here. So because it is 1, 2, 3, 4 and then 5, but as you can see, we appended to the very oldest position, so we need to unrotate it. So what this unrotate does is just simply puts the right order into this list and makes it 1, 2, 3, 4 and 5. So as you can see, if the sequence list is less than the cache, just return it. If the position is 0, again return the cache. If not, just put it into the right order, which is just this simple concatenation, which is technically putting this into the right order, which we need to repeat it each time that we append a new token, for example. But the main part and the main class, which is cache view, so what it does is simply gives a view into a particular layers, key and value cache tensors, and it just handles the whole returning the correctly interleaved keys and values. Again, I'm gonna do a quick pause here, and then we're gonna get into much more detailed example, numerical example, which you can easily understand that what's exactly going on in this cache view class. So imagine we have the cache key and value and metadata. Metadata is very important. Again, don't forget what was the metadata and what we had in metadata. And KV sequences, it's just the sequence of the whatever we had in the cache. So update, how update works and what it does. As you can see here in the stock string, it writes the new key and value tensors into the cache using the cache positions from that metadata. What it does, it just simply flattens the cache and values. We keep the number of heads and head dimensions, and other than that, we flatten the KV, and we try to just add the new tokens, let's say, into the into the right positions. And then what we do, because we have the new tokens, we interleave them. And again, do not forget what interleaved means. We need to put and append the right tokens, the tokens into the right sequences. Again, we will see them in a minute, what it means. And after doing the interleave, we need to unrotate them, because again, this logical sequence of the new tokens, when they join into the buffer, it's a bit problematic. We need to do that on rotation, and once we did on rotation, we can just send it back to the rest of the calculation. So I know it's a little bit hard, and I'm not sure if I explained it in the best way possible, but hopefully with this example you can understand it much better. So what I do, we have technically 3 passes here, but I'm not gonna do the first one. The first one is more high level and high overview, which you can go and have a look at it. I do the second one, which I would say it's more, I can say, compact, but also informative. So let's go to this part, comprehensive real world example for, let's say, chatbots, and hopefully if this works. I never tried it. Okay, Now imagine what we have. Imagine we have 3 conversations. These 3 conversations, we give them all into the system. And imagine the first conversation is just a technical report, the second conversation is product inquiry, and the third one is just billing question. The initialization could be something like the prompt, or imagine we are in the middle of a conversation, for example. So whatever that it is, the first conversation is 50 tokens processed by now. The second one is 8 tokens, and the third one is 22 tokens. So as you can see, and it is clear, the batch size is 3. The maximum sequence length is 128. So each of these conversations could not be more than 128 size in the sequence. So we have 3 sequences. Each sequence is max 128 length. Number of KB heads, let's say it's 4. And the head dimension is 32. And let's say the new token per step is 1, which is just for simplicity. It's not necessarily like that. So the initial step. So right now in the code, if I want to say, we are technically in the cache view, we are right here. We get the tokens and the cache values, and we have the new values, and we want to flatten them and then update them and then interview and unrotate them. But right now we are in this part. So what happens? We have cache, k and value, and the sequence length is, again, do not forget that it was 50, 8 and 22. So technically the cache tensor would look like 3 sequences, each with a max sequence length of 128, head dim of 4, each head contains 32 dimension, and the same for the cache. And again, about the 3 positions, we have, for the first conversation, we have 15 up until 127, for the second 8 to the rest of the sentence, and for the third conversation we have 22 up until the 127. Now imagine that we have a new user message. So the first one, which was, what was that? It was technical support, product inquiry, and billing question. And now imagine the next token for the first one is what, for the second one is how, and then when. So how they look like technically, because we have a batch of 3, so they look 3 by 4 by 32. Hopefully that makes sense why it is like that. To cache max, if you remember, so right here in the metadata we had something called to cache mask and cache elements and cache positions. Remember them? To cache mask allows us to say that, okay, whether I want to cache it or I want to mask it and just kind of don't look at it. So when we say true, we will attend them and we will look at them and we will bring them in our calculation. And the cache positions, it is 15, 8, and 22. And it is clear why, because these are the next 3 positions. So the first one here was 15 tokens, so that would be from 0 to 14, from 0 to 7, from 0 to 21. So the next positions when the next new token comes would be 15, 8, and 22. And the sequence length again is 1, 1, 1, because there's only 1 token which comes, but that's not necessarily true for real systems. It could be much more. For example, it could be 3, 10, 12, whatever. Just imagine when you write something to a chatbot, it could have different lengths. This is that part. And now what we need to do is we need to extract the dimension and flatten them. If you remember again, right here we had the flattening part, which I need to have just the heads and head dimension and then flatten the rest. So head dimension, flatten the rest. And the reason why we do that, you'll see it in a minute. So okay, now when we flatten those, we know that for the conversation 1, position 15, the flat index of that would be 0 times 128 plus 15, which is 15. But for the second one, that would be 1 times 128 plus 8, which would be 136. So you can technically see it something like this. Previously we had, let's say 3 sequences, which one of them was fill up until 14, one of them was all the way up to 7 technically, and they start from 0. So, and the other one was from 22, because we flattened them. So now we have something like very long tensor, and this is very ugly tensor. This is the first one, second one, and third one. So technically, when we want to append the new tokens, we now see that, okay, that this new token is 15, which is somewhere around here, 160, 136, which would be something roughly here, and 278, which is roughly here. And the reason why we flatten this, I know it might look a little bit silly, but it's just the computation and those tensor product and multiplications, which is more optimized technically. So yeah, so the flat cache K15 would be the new token for the first conversation. The position 136 would be the new token for the second conversation, and in the flat cache, the position 278 would be the new token for the conversation 3, and the same for values. So now what will happen, the KV sequence lengths, they changed. So we have 16, 9, and 23. And now imagine that we calculate the next token from our attention, or whatever that it is. So technically that's the next step. And we make the xk attention and xv attention. So again, because it is one token, it is the same tensor with this length, 3 by 4 by 32. Again, 4 is the head time, and 32 4 is number of heads, and 32 is the head dimension. And again, if you remember right, where was it? I think it was, yeah, right here, when we do the splitting, why we do the splitting and interwheeling, if you remember. So we have these 3 tokens, but we need to split them and make them look like this: 1 by 4 by 32, 1 by 4 by 32, and again 1 by 4 by 32. And now what we need to do, if you remember again from this interleaving part, whatever it was, we need to append them in the right order. That's why we need this function. We split them, we have 3, it is exactly like x, y, z, and previously here we have that a, b, c. So we interleave them, and where was it? Yeah, right here. And then we can split the tokens, unrotate them, and then put them back together. So this is technically, and yeah, here, do the concatenation. So this is technically how it looks within a numerical example. And if you want even a further detailed example, you can go to the next round, which is ultra detailed example, and it literally gives you even the numbers, that how they look like and at each position. And when we do the appending, or I don't know, rotating, so on and so forth, how it looks and how it happens. So this is very in detailed. I spent a lot of time to make this. So yeah, I will put it in my GitHub repo and go there and have a look at it. And yeah, technically that's how it works. And this was for this section, which was the sliding window attention, the cache, everything about caching, KV cache, and rolling buffer. And just a quick one, and the last thing, that where that cache and will be used technically, as you can see in the transformers layers, again in Mistral code, we have this cache view right here, and where we use it is technically right down here in the forward pass, and we will give it to the forward pass of the attention. And yes, so technically I would like to add something else to this video, which is grouped query attention, which I can quickly explain. I think that would worth mentioning. So about the just imagine when we have the query and values. So for each query, what we can do in a simple attention, for each query we have one key. So this is the simple format, but what we can do in order to make it even more optimized, for each two query we can have one value, which, so technically they share the value, key or value, and this is called group query query attention, which makes it much more optimized. Or we can even have, I don't know, for every tree we can have one key or value, or even furthermore, if we have one key or value for each query, that's the simple one. If we have something like this, let's say if we have, for example, for each 4 we have one key or value, this is what's called group query attention. But if we have only one, this is, I think, called multiple query attention. And this is just kind of repetition within the keys and values. And on the code where you can see it, again in the transforms layers, if I can quickly find it, so it should be, yeah, right down here in the code. Again, in the next section, when I'm writing the whole code, you can see in more detail that how it looks. I just wanted to give a full quick explanation of how it looks, because it's very simple. It's just repeating the keys and values. There's a function called repeat kv, and what it does simply is just if I can find it right here, it uses a torch function, which is repeat interleave, and it repeats the tensor cells in a dimension, in a given dimension. So how it looks in code in a numerical example, so here, as you can see, imagine that I have a tensor of 1 2 3 right here. If I want to interleave it 3 times in the dimension, I think that would be 0, that would be 1 1 1 2 2 2 and 3 3 3. I just repeated. So it's exactly the same as, again, this visualization. What I do is just I have the tensor and I just need multiply it, just use the same thing, so it avoids furthermore computation. So for example, again, I have 1 2 3, and I want to, let's go for this third example along a specific dimension. Imagine that I have 1 2 3 4, and I want to do the repetition in dimension 0 2 times. So that would be 1 1 in dimension 0 that would be 1 2. Then I will repeat it again because it's dimension 2 3 4. I repeat it again 3 4. But if I do it in the dimension 1, that would be 1 1 2 2 3 3 4 4. So hopefully you have a better understanding of how this repeat KV works down here. So yeah, this was the code and explanation for the sliding window attention, rolling buffer, group query attention, and what was the other one? KV cache. And hopefully it was informative for you. And again, I will put all this material, PDFs and visualizations in my GitHub. Feel free to have a look at it, and don't forget to like and subscribe to the video. And yeah, okay, in this part I'm gonna talk about LORA, which stands for low rank adaptation. And the reason that I want to talk about it, because so first and foremost, it is on the code itself, it is on the Mistral codes itself. And the other one is when you want to do kind of fine-tuning for Mistral, it is very useful, and we can do this fine-tuning with LORA in fact capability. But first of all, what this LORA is, stands for, as I said, low rank adaptation. And what it does technically is, just imagine, we know that all layers, they are kind of matrices, a learnable matrix. So when we fine-tune, we have two options. One of them is just simply do the fine-tuning of the whole layer, all the parameters of the original weights. But the other way, which is a kind of trick, which is very useful, is that we can freeze the original weights, and we can add two additional matrices, which we call it A and B, and train them and freeze the original one. But the thing is, the rank of these two matrices are much lower than the rank of the original matrix, which will help us a lot in terms of number of parameters to learn. So what we do is we have A and B, and they are all learnable. The rank is something like, let's say, R. So one of them is, let's say, I don't know, R by N, and the other one is N by R. So they are learnable, but once we teach them, they will learn, and then we will multiply them and then add them to the original weight. So how it looks in terms of mathematics, as you can see, it is just simply, we have the original weight, and we have this delta W, and delta W is A and B, those two matrices, and A is, and by the way, we need to remember that W is in, the dimension of W is D by K. So A is D by R, and B is R by K, which R is much better, much smaller than D and K, minimum of both of those. So which will help us a lot in terms of, in fact, parameter efficiency and computational efficiency, as you can see here, for the fine-tuning. And we will have an example of how different it looks and it can be. So it is something around 32 times lower in terms of learning parameters, which is amazing. But a little bit, a quick analogy of the in fact, LORA fine-tuning versus the standard fine-tuning. Just imagine you're a kind of violinist, and you are, I don't know, skilled in your own specific way or specific, I don't know, field. And what happens now is your composer wants you to slightly adapt a new style and perform for one performance. So, and you don't want to retrain yourself completely. there are two options. Yeah, one of them is retrain completely, you forget everything and you learn from scratch all that style for that specific, let's say, performance, which takes a lot of time. Just imagine how long would it take to be a violinist. The other one is just imagine, I don't know, the composer or the orchestrator will give you a few small note cards, which technically is the low rank matrices A and B here. And it is just a few tips and points about how to do for that specific style and perform for that specific style. For example, add a soft vibrato here, I don't know, play this part slightly faster, emphasize this note, so on and so forth. This is exactly how low rank adaptation would look like. It's a kind of maybe cheat sheet, or I don't know, a small note cards for the model, which can help that to learn in a specific direction. For example, you have Mistral, but you want it to be excellent at legal. So you can do the low rank adaptation and fine tune it on legal, takes only, or I don't know, it could be biological data or whatever that it is. And a small example here, just imagine we have the weights, original weights are in the 512 by 512, which are the original weight. Low rank, we put the R equal to 8, so the A and B would be 512 by 8 and B would be 8 by 512. So when we want to teach the model, when we want to do the training, if we do the standard one, we have to do the whole training for the original weights, which is 512 by 512, which is 262,000 multiply in adds and learnable parameters. But if we do it with LORA, it is simply just this tiny bit of training and parameters, which is equal to something around 8,000, which is 32 times less, which is just amazing. But in terms of, and this is just a quick example, you can have a look at it, stop the video and have a look at it to better understand it. So in terms of accuracy, this is a very important part. For that specific data, it is high and full accuracy, which is great with that little amount of parameters. So you can do the training fast and furious, but have still the same accuracy. And when we say the accuracy, it depends on the alpha in fact parameter. Alpha parameter allows you to say it's just a parameter, you can multiply that by A and B, and it tells you that, okay, tells the model by how much forget your previous data and by how much adapt the new data. So you can, it's kind of importance factor. You can tell the model that, okay, be more adapted to this new data. And yeah, that's technically how it happens. And we will talk about the state dictionary in a moment, but let's just quickly go to the code and see how it happens. And by the way, these are all, again, I emphasize, these are all from the Mistral code, Mistral Inference GitHub. What I did, I just add more explanation and comments around it, and I will explain them line by line, and I will put it into my GitHub. Feel free to go and have a look and see how is it going, and if you have any questions, just put it on comments and I will do my best to answer them all. So on the transformer layer, so as you can see, we have this LORA args, which is just a bunch of arguments, which we will go back and we will I will explain them in a minute. And the other one is LORA linear. So it is just what it says basically is that we define another function which is maybe LORA, and what we say is that whether user will prefer to do extra fine-tuning or not. So they can say, okay, I want to have this LORA from maybe LORA, or no, just simply return simple linear layer. So what it does is for all, literally for all linear layers in Mistral, you can have this. You can choose to have it in a fine-tuning manner or just as it is. For example, if I just click on this, maybe LORA, so as you can see, we have it for all here in this attention part. We have it for all these linear layers in Q query and value and output, so you can retrain and fine-tune them, or even in the feed forward layer, as you can see, we can define them as maybe LORA. So as the name suggests, it is maybe LORA. If you want, it is. If you don't want, it's not. But what these two, LORA argument and LORA linear, what are they? So here in LORA, the Py script, what we have is just a bunch of imports, and then we have LORA arguments, which is rank, which we saw here, which was technically the R right here, and the other one is the scaling vector, which is that alpha, which literally tells you that by how much our data is important, and by how much the model should pay attention to the new data and give more importance to the new incoming data that we want to do the fine-tuning. And yeah, so that's also a data class. It's just a bunch of arguments. So the LORA linear, what it does is just this module, as you can see here, adds trainable low rank decomposition LORA on top of the frozen linear layers, as we saw in the attention and the feed forward layer. So a bunch of arguments, input features, output features, rank, and scaling and bias. We initialize them, we add them as self, and then what it does is literally we define that A and B matrices, which we had it here with the rank that we defined, and we can simply add them to the model. So for this part, which is, I would say, in this file, in this script, these lines are maybe the most important one, these 2 or 3, which, as you can see, it is just a post hook for getting some of the or let's say dealing about missing LORA weights, and we will see, just bear with me, we will see what this means and why we should kind of handle this error. And yeah, here again, the rest of it is just a bunch of, it's just a forward pass which tells you that, okay, how we can just add these LORA weights to the original weights and update the state dictionary and give it back to the next step. But what is a state dictionary and why we should here ignore missing keys in a state dictionary? So for those who don't know what a state dictionary is, so a state dictionary, so when we train a model, we can save the weights, and these are all in a file. It's a simple file, it's kind of dictionary which literally tells you that, okay, this is the, for example, the key, it is a key and values, and the keys are technically the layer names and values are the tensors or those matrices which they've been trained. So for example, as an example, just imagine that we have this very small model. We have one linear ReLU and another linear layer, and model.state dictionary would be just 0.weight, 0.bias, 2.weight, 2.bias. Why we don't have 1? Because 1 is ReLU, and ReLU doesn't have any learnable parameter. So these are all the parameters that we have for that specific model, or for the case of, for a more complex case, an attention, let's say simple attention layer. So as you can see, we have Q project, K project, and V project projections. This is technically how the keys for the weights they look like, which we can use them in order to fine-tune the model. And what exactly happens in that part of the code that I mentioned. So this was just explanation about the state dict, but we had a part here back in the code, original Mistral code, that says ignore missing keys. Why we should have missing keys and why we should ignore them. It seems like a little bit funny that why we should ignore them. So the thing is, the whole purpose is if some parameters are missing, first of all, PyTorch will warn or throw an error. Imagine that we train the model, it has 4 layers, and when we load the state dict, it has 3 layers, so it will throw an error that, okay, I don't have one more layer, what's going on? So what happens here, as you can see, we're emptying the list of the missing keys. But why is this happening? So imagine in a case of in a numerical example, imagine that we have this LORA linear. We have LORA A, LORA B, and linear. So technically, the expected weight when in the model, in the original Mistral model, when we say that, okay, use LORA, this is how it will going to be look like, and this is how the model expect the weights to be. And when we load the checkpoint, we don't have those LORAs because we want to fine tune them, because we didn't have anything in the first training. We don't have any LORA, but now we want to do a fine tuning, so we have some LORAs. So when we load the checkpoint, it doesn't have any LORA, and it throws an error and says, okay, what the hell is going on? I don't have these two LORA B weights and LORA A weights. And we say, okay, I know that because I added them. So just silence the model and then add those two into the state dict gradually. So this is exactly, and this is all that happens. So these layers will just keep their default initialized values, and we will add them later on because we don't have them. So by doing this, we kind of prevent the model from throwing an error. So, and yeah, so further on, if I want to, I don't know, there's nothing here. This is more just a concrete example which you can have a look at it. And yeah, so again, to summarize it, we know the truth. Those layers, they don't exist during the original training, and they are the new layers which I added because I want to do the fine-tuning. So it's correct that there are no LORA weights in the file. What I want to from the model to do is just, okay, forget those errors and add them while we train, add those into the state dict while we do the training. It's just a simple error handling, I can say. So yeah, this is exactly what happens here. And then we add, as you can see, we are populating the, right here, we are populating the state dict with frozen weights and dummy LORA weights because we don't have any weights. We put them together. And then what happens in LORA loader mixin is simply, I'm not going to explain this too much in detail because it's easier to understand. What it does, it will just do a couple of checks to make sure that data class data and the layers, data types of the layers are consistent and they are in the right device. For example, it will check to load the path if it exists. If not, just throw an error. I don't know, further on, just for example here, when we want to load it, it will check the consistency of the data types. It will check all the layers, and for each layer it will check the data type, and if there is any inconsistency it will raise an error. And again, if the data types are compatible between model and those dummy layers, added layers, and I don't know, further on, if they are in the correct device, and so on and so forth. And then replace the eligible linear layer with LORA enhanced weights, which are very useful in the fine-tuning phase, and the rest of the thing is just a bunch of adds and multiplications, which are easy to understand. And yeah, technically this is how this LORA linear works, and we will use it on literally all the LORA in fact linear layers in Mistral. And yeah, this was the LORA explanation and how it's being used in Mistral. Okay, this part is about a mixture of experts, and I know that sometimes it doesn't necessarily, so Mistral doesn't necessarily have mixture of expert, but Mistral definitely has that part. But the thing is, according to code in Mistral, if you go and have a look, we can just do it quickly here. So if we have a look at transformers layers, we can see that in this block, I think it should be right here. Yeah, in the feed forward part, as you can see, we have a kind of MOE checker which checks if we want this feed forward layer to be a simple in fact feed forward or a mixture of expert layers. So that's why I'm gonna cover a mixture of experts here in Mistral. So what it says, according to this diagram, as you can see here, just imagine that we have transformers, vanilla transformers, and mixture of experts. What happens, everything is the same in input and encoding. Let's say the decoder block, layer norm, mask self-attention, and again another layer norm. But what happens is exactly in this part. So in transformers, what we have after all those calculations, all those will be given to a feed-forward network, and this feed-forward network will, it could be, I don't know, classifier or whatever that it is, it will make some decision and it will output whatever the output is into the decoder block. And it is just simply a very big, giant feed-forward network, which has lots of parameters. But the thing is, imagine that you're in the inference time, and this network is too big. Why you should do inference each time on such a big network to make some decisions? What you can do, maybe, instead of a very giant network, have a couple of smaller networks, just like here in mixture of experts, which each of them are expert in a specific field. And imagine that you have another small feed-forward network or another logic, which we call it router or gate, which can decide which of these experts need to take care of that incoming token. So imagine it in this way. Imagine that, I don't know, you want to talk about something, or the input token is about, let's say, any topic. You can give it to a very big network, which is expert in all the fields, but it has lots of parameters. But the other thing that you can do in mixture of expert is, alternatively, you can do this. Take a look at that input token and decide which of these experts are the best to handle and deal with that incoming token. So what's the benefit? The benefit is you don't need to activate all these experts on inference time. You can, let's say, you can specify top k, let's say top k equal to, and you can say, okay, just 2 experts look at that incoming token. So the thing is, you have the same strength in the model because you have lots of experts. It's the same as this giant feed-forward, but you don't need to use all of them, which means you are much more optimized and you don't need to, you don't need to burn lots of GPUs for that. So yeah, briefly explaining, so mixture of expert is just a type of neural network architecture that is dynamically, this is important, routes input data through only subset of specialized modules. We can call them experts. it's just inspired from humans that they delegate tasks to each other. And yeah, I explained about these gate and top case, so on and so forth. But about the analogy, and this is a good analogy, I would say. Just imagine that when someone is, I don't know, sick or whatever, imagine that the guy goes to hospital, and hospital has lots of doctors. You can't go and talk to each of them. So what you do is you literally go to receptionist and you explain about your problem, and receptionist, which is gate here, just routes you through the best doctors. So yeah, that's how it works. And also it's worth mentioning that the top K experts can tell us that our version of the mixture of expert is sparse. If top K is, for example, the K is 2 or 3 or 1, or if we use all of the experts, that would be dense mixture of experts, or sometimes I think they call it soft mixture of experts as well. So a very simple example of that would be something like this. It's very simple, not neural networky. It is just imagine that we have 3 experts and these are returning, let's say, imagine if it is the input is x, it returns x plus 1, expert 2, x times 2, x to the power of 2 is the third expert. And the gate would be something very rule based, and if x is less than 2, do something. If it is less than 5, do something else, just do something else. So this is technically the logic behind it. Very hard coded. But about a more advanced example, I can say a sparse mixture of experts with top K gates. Imagine that we have 3 expert neural nets and we want to do a top 2 experts. So what we have here is we have the expert initialization, the expert class, which is just simply a linear layer, or just simply a feed forward with input size and the output size dimension. The feed forward is just literally just giving the tensor into that expert. The gates are just the input size, and the output size is number of experts, because we want to see that in that tensor we want to have the logits and or softmax to decide which agents we need to choose and which agents we need to route the input further on. So we initialize the sparse mixture of experts. We have the experts themselves, the top K, in fact the layers of the experts, and initializing the gates. So what happens technically here is we just simply give the inputs to the gate, and then gates decides that, okay, based on that top K, because gate is a learning neural net, feed forward net. So the gate decides that, okay, what are the top K guys or experts who can, I don't know, fix this problem or deal with this token, input token. It will just give us the indices, and we can do the softmax, and I will tell you why we do logits and softmax as well. And once we have all those experts, we can route and give the input token to those experts, and then based on the weight that we have from the softmax for each of those experts, we can weight their output. Imagine it's just the same as saying that, okay, you have 3 doctors and one of them is really specialized the best. So whenever you have, I don't know, for example, you have a headache, when the best doctor tries to diagnose that, you give more weight to what he says to you and less weight to the 2 others. This is exactly what happens, and why we have these softmax weights. Once we give the input token to, let's say, 2 experts, we give also the weight to their decision, and then we calculate whatever the output is. So yes, this is technically why we're using logits as well as the softmax. So we use them because we want to weight the decision of the experts, in short. And also the other question is, I don't know, if each token is processed by its own expert or a few experts, how the hell they know what's the context of the full sentence. So the thing is, once we give the input to the experts, they have already passed from the self-attention. So they do have information of the whole context and sentence. So there is no need to worry about anything like that. Just a quick look at mixture of experts code, which is derived from Mistral GitHub repo. I just add more comments and explanation to easy understand that, and I will put it into my GitHub repo so you can have a look at it if you like to learn more. So what it does, we have a bunch of inputs, imports, and then we have a MOE args, which is a data class, and it simply defines has the number of expert as integer and the number of experts who will be given to each token. So how many experts need to make decision about each token. So technically this is the same as top K. And then here in the MOE, a mixture of expert layer. So what we have simply, this is just the same as what we saw in the previous code. We have a number of experts, which is just a module list and full of experts, which could be neural nets, and so on and so forth. And we have the gate, which is also another neural net, which decides to which experts route the token to, and the arguments. And simply what we do here is just we initialize the gate and we give the input and we get the logits. Then we do the top K based on the number of, in fact, top K or number of experts per token, which we defined in this data class right up here. And then again, because we want to weight the decision of each of the experts, we do a softmax and we put them into a, let's say, list or tensor, whatever that it is. And then in this for loop, what we do is technically, now we have the experts. We give the input to those experts. They will tell us about their decisions, and then we multiply those decisions to the weights derived from this softmax weight, and then we have all the results. Yeah, so this is technically how the mixture of experts works. And as I mentioned, if you go to GitHub of Mistral, you can see that in the so this is the file which is called transformer layers. They have something called feed forward, self.feed forward, and they decide, you can decide that whether this feed forward could be or should be simply a simple feed forward with LORA, which we will talk about next, or we can decide it to be mixture of expert layers. And yes, that's it for mixture of expert